Good morning again. Right, so now we move on to chapter 2.2, that's settlement. I do apologize, my bad voice, having a very bad cough and sore throat. Okay. Right, here we go. When we talk about settlement, we are really talking about a situation where the soil under load is going down slowly. That's the key word, it's going down slowly. And as most civil engineering structures are founded on soils or rocks, this load is going to cause it to settle. And the settlements we are talking about could be excessive or non-uniform. And just to bear in mind, when you say excessive, it simply means that there's too much of settlement. The soil is, any grounds, any soil is always subsiding, always settling. Right? We will learn after this one that is the case. However, when it's excessive, meaning that it's exceeding a certain limit that we permit for the structure or embankment, right? But if it's non-uniform, most of the time, in the case where it's a non-uniform settlement, it is more serious and the risk is higher, because when it's non-uniform, imagine a building, on the left it is setting 10 cm, on the right it's setting 20 cm. So the differential settlement is going to cause the structure to be under stress because concrete, right? And you will start seeing structural failure on your building or your roads or whatever superstructures that is founded on that kind of soil. And in order to analyze settlement, we look into several factors as listed down there. You can see what is the magnitude of the stress that you apply. Obviously, a big load or small load, geometry of the planned area, depth of the stress being applied. It has got to do with the width of your stress area and the thickness of the compressed soil stratum. You will be probably asking why only the width and not the length. Now, in our settlement analysis in this chapter, that is for two-dimensional approach, meaning that we assume that the settlement is happening in the soil that is being looked at from just the front cross section, meaning that we don't take into consideration the length of the soil concern towards the back, meaning that you have the x-axis, you have the z-axis, the y-axis that is going outside the screen or towards the back. That's the third dimension. We'll omit that. Right? And number 4 is about the compressibility of the soil stratum. Apparently, if the soil is more compressible, for example, clay, and you have a separate site with sandy clay, so we should be suffering more compressibility, meaning that when you put the load, it will go down more. Well, even without learning geotechnics, without learning this chapter, you'll be able to answer that it should certainly be the clay. And in this chapter, later on, you'll see why. Alright? And finally, the rigidity of the foundation. This is an interesting one because most of the foundation, let's say, is a pad footing. We say that it's made of concrete, right? So we take it as the concrete is such a rigid and firm structure that it's not going to be flexible at all. Nonetheless, the truth is almost all structures are flexible. And when it's flexible, you can imagine when you load it up, it is going to form a small curve, right? A curvature in the middle of the loaded area. So this curvature is going to change the way the stress is being distributed into the ground and change the way that the soil is going to bear the foundation. Anyway, it's not something to be worried about, because in our first approach to learn settlement, we are not going to consider those complications, right? But it's important to know the factors you need to consider when you're trying to do a general analysis on settlement. Good. Right, look at this diagram. It's in your module as well, in figure 2.13. You'll find that the influence zones of your soil that is being loaded from the top will be changing, or rather will be taken down to the depth of where you put your foundation. Because remember, the purpose of the foundation is to bring your load that's being applied from the top to the ground, to the level, to the depth that you want the soil to take the load. So just look at the first one. These are isolated pad footings, simple shallow footings. You can see that the influence zone is pretty much near the surface because the foundation is just very low, very near the surface, is barely 5 meters away. If you have a rough foundation, and you can see that the building now is becoming a taller, multi-story building going up. So a rough foundation is a big, simply imagine a big slab, alright, just a slab covering the whole floor area of your building. And in such a case, the pressure bulb or the stress distribution is going to look like this, right? The influence zone. And similarly now, say my building is going taller and I can't afford to put my foundation that shallow, I bring it deeper, right? And these layers these levels of the building that are underground. We call them basement, and that is very common. Most of the tall buildings will do that, partially to gain space for parking or for more space for retail, for business, or for offices and all. But primarily, the purpose of putting in the basement is to bring the foundation to a greater depth. So instead of just wasting the space, you might as well just use it. That's why they are used as basement. Alright? And similarly, as you can see, the influence zone is being brought down to a greater depth, but the shape and the size is still the same. What if this is a situation of a pile foundation? So as you can see here, if they are isolated, then you have these piles coming down, and each one will have their own each pile group. These are all individual pile groups. You see, inside each group there are 1, 2, 3. From our point of view, there are 3. Probably at the back there are the rows of 5, 6. We don't know. Alright, it doesn't matter. You can see that each group is being considered to have their own individual influence zone. Similarly, if you are having pile groups as such, and the soil is end bearing, meaning that at this level, where the shaft of the pile is, these soils are not able to sustain any load. All loads are being taken at the end of the pile, and you can see that the pressure bulb, the influence zones are being formed like this, at the base of the pile. And the last one here, the last example we are looking at is a caisson, or the wall foundation. This kind of foundation is a huge pipe, and it's empty inside, and it's very commonly used in what? Yes, you guess it. It's very commonly used to build bridges, alright? Penang Bridge, Second Link, and so on and so forth. And how they construct it is that first they have to drop this big, huge, heavy, usually a concrete or a steel pipe into the seabed, alright? Make sure it's aligned, and then they suck the water out. Once the water is out, then you can put the human being in there. You start putting reinforcement, putting the tramic pipe to drop the concrete, and so on and so forth. So it's pretty scary, really. Imagine this is the caisson, and this is the water level. This is the sea. So the person working in here is actually below the sea level. Right? So let's put that aside. That's just a sideline story. Go back to this. Now for a caisson, because it's empty inside, and when the load starts to go in, alright, you can see that the pressure bulb is the same. The influence zone starts from the base of the caisson wall or the foundation. However, because it's hollow in there, you could actually find that there is this plugging effect. Some of the soil push itself into the cavity or this space in the pipe. Whether it's good or bad is debatable. Some researchers say that it's good because when the soil gets into the pipe, there is friction between the inner wall of the pipe and the soil, so that will help to increase the bearing capacity. Some say it's bad because when you do that, you're having a very disturbed area around here, and the air that's being trapped in here, because the soil doesn't go all the way up, the soil will actually, it's a soil plug, right? It's like the sumbat, so it will actually form an air cushion in here, and that air cushion, because it's air, you can't stop air from the escaping whenever there's a small leakage of void somewhere, so it may not be such a good idea. But that is research purposes. If you are interested, you could probably explore that in your PSM later on. Alright, now in order to analyze settlement, we must first know what is the stress like. Stress is simply a load over an area that is being loaded, right? So the problem with, not problem, the thing here with settlement is that we learned before this that we rarely put a foundation on the ground surface. It's always excavated and put down there, or having a pile that being pushed or shoved into the ground. And the reason is simple. One, when you put it on the ground surface, you are subjecting your building or whatever structures that's being erected there to horizontal loads like wind loads, earthquakes, and so on, which could easily destabilize and topple it, right? And secondly, when you dig the soil and put your foundation deeper into the ground, whether you dig to 5 meters and put a pad footing down there, or you push your foundation, your piles into 20 meters, 30 meters deep, then you are making use of the undisturbed soil down there. Plus, the deeper the soil is, the stronger the stratum is going to be. Again, this is common sense. Why? Simply because it is deeper. And it's deeper, meaning that it is suffering, or he has suffered, or he has sustained the load of his friend that is on top of it. Say you're at 20 meters, say you are a layer of soil at 20 meters. You, in order to stay where you are at 20 meters, you must be able to sustain your friend that is bumping on you, that's on top of you at the top 20 meters. Am I right? Yeah. That goes on to explain why certain soils today that you see is only on the ground surface, but it's very strong, very hard. Because previously, probably that area is a mountain, or probably during the ice age, the top of that area is ice, and we know they are heavy. So the soil has a memory, as we will learn in consolidation in the subsequent subtopics. Right. So now let's look at stress distribution first, so that if we can calculate the stress at a certain depth where we want to put the foundation, then only we can start talking about putting the foundation there and expecting it to carry the load that we want it to carry. Right? Now, for stress distribution analysis in geotechnics, there are three things that we need to assume for the soil, and the first assumption is already quite quote-unquote dodgy. That is elastic. We need to assume that the soil is fully elastic. What is elastic? Elastic means that when you pop a load onto a material, the material will deform. When we say deform, means that it will probably be squashed down, but it will be expanded sideways, right? That is squeezy ball. But when you take the load off, it will actually bounce back to its original shape and volume. That is elastic. We all know that soil is not like this, but the first assumption you got to make for stress distribution is that it is fully elastic. The second assumption is that it is homogeneous. Now, homogeneous is a lot more easier to accept, because homogeneous means it has the same properties throughout. At any point that you take in the soil mass, it has got the same properties, same water content, same GS, same liquid limit. That is alright, that's acceptable. Because in general, despite the variation, the soil will have very similar properties across the same layer, right? And the last assumption is isotropic. Isotropic is directional, meaning that the soil has the same properties in the same direction. Typically, we'll cite an example of the permeability of the soil. Permeability, right? The ability of the soil to allow water to pass through it. Now, for example, when it's raining, you have water coming down through the surface of the ground into the soil. That is vertically going down. Then you're talking about the vertical permeability of the soil. And you use the coefficient of vertical permeability, Kv, right? When it reaches a certain depth, when the flow downwards is not so great, it may start to want to flow horizontally, right? So to flow horizontally, it depends on the horizontal soil permeability coefficient, that's Kh. Now, if you say a soil is isotropic, then the Kv and the Kh must be the same. So as you can see here, out of three assumptions, elastic, homogeneous, and isotropic, probably the one that is the one assumption that could be quite quite with the highest possibility of being correct is homogeneous. Whether it's elastic or isotropic, that is maybe a bit debatable, but we just make the assumption. Right, now the first method that we can use to calculate our stress distribution is the Busnes method. So Busnes says that when you apply a point load, right, typically it has to be a point load on the surface of the ground, and you want to know at a certain depth, say Z depth, away from the ground surface, what is that stress increase in there, right? As you can see, delta sigma Z. Stress increase, we are talking about stress being applied on the surface here. When it comes down to a depth of Z, what is the increment here? What is the additional stress caused by P? Why do we say additional? Because before you even do anything, before you even put in the load P, at point A, for example, the soil weight itself is already exerting a certain load, a stress on point A. Hence, we say is increment, right? So Busnes gives this equation, which is actually taking a circle, right, around your affected area. If your point A is directly beneath, then the equation becomes simplified, as you can see here, 0.48 P over Z squared. Right, the second method is a Fadden's method. Fadden's method simply says that it's a derivation from the Busnes method. It's just that it doesn't just consider a point. Right, let's continue in the next video. Right, let's pause for a bit. Thank you.